Yeah, so welcome everybody once again. My name is Ibikunle Ojo. So this is experiment 5. And for this experiment, we are going to be talking about reverberation time. So for this experiment, we have like how many tables? 1, 2, 3, up to 7 tables, which in which we are going to be populating like different data into. So to start off with this experiment, we are going to start with table 1. I have a sketch here. So this is what my racket ball court looks like. So as you can see, it has a dimension of height 6.1 meters, length 6.1 meters, and breadth 12.2 meters. So from this sketch here, as you can see, this is my ceiling right here. Here underneath is my floor. That's the floor of the racket ball court. And here's the front. So here's the front. And right behind this is the back. And here is the left. And the other side is the right. Our area for the ceiling is going to be 6.1, which is the length, times 12.2, which is the breadth. So that will be 6.1 times 12.2. And that is going to give us 74.42. Our effective absorption area is going to be 0.02 times the area of the ceiling, which is 74.42. So I'll multiply this value by 0.02, and that will give me my effective absorption area, which is 1.4884 sabins. Now for the floor. So as you can see, the dimension for the floor, which is here, is still the same as that of the ceiling. Therefore, if we have the area of the ceiling to be 74.42, then the area of the floor will also be 74.42 because their dimensions are the same. So here is going to be 74.42 times 0.1, and that will give us 7.442. So the addition of all the numbers we have here on this column is going to give us the total effective absorption area. That is going to be 13.3956. The total area is going to be the addition of all the numbers you have here on this column, and that's going to give us 372.1. The next in line is table 2. So for table 2, what we have to do right here is to calculate the cut volume. We calculate this value here, which is 0.16 times the cut volume V, then the total SC for table 1. So we've already calculated that to be 13.3956. So I'll put it down here. And then we calculate the reverberation time using the formula here. So to calculate your reverberation time, that's going to be 0.16 times the cut volume V divided by the total effective absorption area. So now to calculate the cut volume, so as you can see, the shape here we have is the shape of a cubeboard, and the volume for a cubeboard is length times breadth times height. So the length of our racket ball court is 6.1, the breadth is 12.2, and the height is 6.1. So when you multiply those three numbers, you have your volume, and that will give us 453 453.962. So that's the cord volume. So 72.63 is my 0.16 times cord volume. So that's that. Now to calculate the reverberation time, we are simply going to divide what we have here, which is 0.16 times V, which is the cord volume, by the total SC, which is what we have here. So our reverberation time is going to be 72.63 divided by 13.3956, and that will give us 5.42. So my approximation is to 2 decimal places. So my reverberation time is going to be 5.42 seconds. Yeah, so that's for table 2. So we move to table 3. So for table 3, we've calculated the cord volume, so we just put it down here. We calculated it to be 453.962, then 0.16 times V, which is the cord volume. We calculated it to be 72.63. Then the previous SC is the total SC, which we calculated here in table 2 and table 1, and that's going to be 13.3956. Now the area of the door is, so as you can see from the sketch I have here, you can see the dimension for the door. You have the length of the door to be 2 meters and you have the breadth to be 1 meter. Therefore, the area of the door is going to be 2 times 1, and that's going to give us 2 meters square. So now the total SC. So we want to calculate the reverberation time of this racket ball cut when we have the door to be open. So when you have the door to be open, your alpha is going to be equal to 1. So to calculate the reverberation time, we have to first of all calculate the total SC for when the door is open. So our alpha for when the door is open, which is 1, times the area of the door, which is 2. So alpha times area. So we have alpha to be 1 times the area of the door, which is 2. And that's going to give us 2 sabins. So we are going to add these 2 sabins to the previous SC. So by adding these 2 sabins to the previous SC, we will get the total SC for when the racket ball cut is opened. So that's going to be 13 point. That's going to be 13.3956 plus 2, and that is going to give us 15.3956. So 15.3956 sabins is the total effective absorption area for when you have the racket ball cut to be open, or when you have the racket ball cut to have an open door. So that's that. So the TR, which is a reverberation time for when the racket ball cut has an open door, is 72.63 divided by 15.3956. So that's going to be 72.63 divided by 15.3956. So our reverberation time is going to be 4.72 seconds. So 4.72 seconds is our reverberation time for when we have the door to be open. So having done what we have here on table 3, we are going to move to table 4. So for table 4, we have the estimated area of the door to be 2 meters square. The number of people in the court is 30, while the estimated area covered by the material is 40.13 meters square. So that's for table 4. So now we move to table 5. So for table 5, we want to calculate the reverberation time for these conditions. So the conditions are cut noise, cut slapstick, door open noise, door open slapstick, and so on. So to do that, we don't have to kind of generate any results. We already have our results here. So what we need to do right now is just to read out our results from the graph which I have with me here. So as you can see from the graph here, we have cut noise, the graph for cut noise. We have the graph for cut slapstick, door open noise, and so on. So I'm going to be reading out the values from this graph in order for me to get my reverberation time for each condition. So starting with cut noise. So if you look at this graph, I have my decibel to be on the y-axis, while my time to be on the x-axis. So my time is in seconds, while my sound intensity, which is on the y-axis, is measured in decibel. So from this graph, to calculate the change in time and the change in decibel, all I need to do is just to find the slope of this graph. So to do that, I'm going to locate 2 points on this graph. So therefore, I'm going to be looking at some points on this line graph that will give me exact values. So now, from this line graph, I can pick these 2 points. So I'll pick this point here and this point here. So I'm going to trace this point to the y-axis. So the first point here is 60 on the y-axis, while the second point here is 80. Therefore, the change in decibel for cut noise is going to be 80 minus 60, and that is going to give me 20. So now I'm going to trace these 2 points down to the x-axis. So if I trace down the first point, which is this one, I'm going to get the time here to be 3 seconds, while for the second point, if I trace it down to the x-axis, I'm going to have the time to be 1.5 seconds. Therefore, the change in time is simply going to be 3 minus 1.5, and that will give me 1.5. So the change in decibel divided, or the change in time divided by the change in decibel, is going to be 1.5 divided by 20, and that will give me 0.075. So 0.075 times 60 is going to give me the reverberation time. So to calculate the reverberation time for the data we have here on this table, we are simply going to use this formula, which is the change in time over the change in decibel times 60. So by multiplying the number I have here by 60, I'm going to get the reverberation time for cut noise to be 4.5. So that's going to be 4.5 seconds. So we move to the next one, which is cut slapstick. So for cut slapstick, I have this to be the graph. So looking at this graph, I can pick these 2 points. I can pick the points here. So the points here and the points here. So if I trace this to the y-axis, I have here to be 60 and here to be 80. Now, if I trace this first point to the x-axis, I'm going to have it to be 1.5 and here to be 0. So now, 80 minus 60 is going to give me the change in decibel for cut slapstick. And that is going to give me 20. While 1.5 minus 0 is going to give me my change in time. And that will be 1.5. So when you divide the two numbers, it's going to give us 0.075. And using this formula, which is change in time divided by change in decibel times 60, you are going to get the reverberation time for cut slapstick to be 4.5. So I'm going to end the population of my data into table 5 here, and I'll leave the rest for you guys to do. So we move on to table 6. So for table 6, you fill in the value for the parameters here. So cut volume, we've calculated it earlier, and we got that to be 453.962, and 0.16 times V, we calculated it to be 72.63. So now we move to the next table. So for the next table, white noise, experimental TR. So that is what we calculated here. White noise experimental TR is what we calculated here, which is 4.5 for 2 people only. So that's what we calculated here, 4.5. Then experimental TR for slapstick is also what we calculated here, which is 4.5. So the calculated SC. So right now, if you have the TR to be 4.5, what is your SC, which is your total effective absorption area, going to be? So to get the value for your SC, you are going to use this formula here, which is 0.16V divided by TR. And that will give us 16.14. So here also is still the same thing, since we have 4.5 here. So here will also be 16.14. So experimental TR for many people. So experimental TR for many people. So that's going to be people in noise. So people in noise, we calculated the TR to be 1.5. So I'm going to leave this one blank, because after you get the value for the people in slapstick, after you get the reverberation time for people in slapstick, you're simply going to bring it here into this table and then make your necessary calculation, which is calculating the value for SC. So right now I'm just going to proceed with calculating the SC for many people in white noise. So this, let me put it here for you to solve. For you to solve. So that's what you are going to do. So now, if I have the experimental TR to be 1.5, then what will be my SC? So using this same formula, my SC is simply going to be 72.63 divided by 1.5. And that'll give me 48.42. So that's going to be 48.42. So the difference in SC is going to be 48.42 minus 16.14. 48.42 minus 16.14. And that'll give me 32.28. So now, number of additional people. So the number of people in the court is 30. Therefore, your N right here is 30. So if your N is 30, which is the number of people in the court, what is going to be N minus 2? So N minus 2 is going to be 30 minus 2, and that will give us 28. So that's that. So the next one is going to be SC per person. So SC per person, so the SC for 28 people is 32.28. So what's going to be the SC for one person? So the SC for one person is simply going to be 32.28 divided by 28. And that will give us 1.15. So I approximated to 2 decimal places. So that's that. So following this same procedure, you do that of slapstick. So I'm going to leave it vacant for you guys to do. So the next one is table 7. So the chord volume is 453.962. 0.16 times V, that's 72.63. And without material, experimental TR